Welcome to today's webinar. Our topic today is understanding coverage in wireless LANs, and we're going to be covering some very important concepts. First of all, the fact that coverage is still important. We can't do away with it just because capacity is needed. We still need coverage where we need coverage. Secondly, coverage is not simple, and we'll talk about this as well. It's important to understand that coverage is the foundation of capacity. You certainly cannot have capacity in a given area if you don't have coverage in that area. And, of course, coverage is technical. So we'll go into several of the technical aspects related to coverage today. First of all, a reminder of what we do here at CWNP. CWNP offers career certifications in enterprise Wi-Fi technologies from beginner to expert. We have not listed on the screen here the CWTS certification for entry-level wireless LAN professionals working in the help desk, working in call centers, sales careers, things of this sort. And then we also have our foundational certification that can take you on to professional level expertise of the CWNA. CWNA is the Certified Wireless Network Administrator. It is required to become a security professional, a design professional, or an analysis professional. And so CWNA is a prerequisite to CWSP, CWDP, or CWAP. Now you can take your CWNA and then take your CWDP, or you can take your CWNA and then your CWAP. There's no specific order professional level exams have to be taken in. A professional level exam successfully completed does renew your CWNA. A professional level exam successfully completed does not renew other professional level exams. They have to be renewed at this time by retaking the exam or by achieving your CWNE status. The CWNE on the screen here is the one listed that does not require an exam. Instead, it requires that you've already passed the CWNA, CWSP, CWDP, and CWAP, and then you submit an application proving 3 years or more of enterprise wireless LAN experience and showing your knowledge of wireless expertise. For more information about our certifications, of course, you can visit CWNP.com. Additionally, I want to make sure that you're aware that we have our conference coming up September the 28th through the 30th in New Orleans this year. And with the code of Wi-Fi Jazz at time of registration, you can save 10% on registration costs. In addition to the conference itself, which will have many excellent speakers over the period of the days, we also have pre-conference training. For example, there's CWAP training and so on. So you can find out more about the pre-conference training, the speaker lineup, and the conference by going to cwnp.com/NOLA for New Orleans. And I look forward to seeing you there. Now let's talk about the first fact that we want to address in this presentation today, and that is that coverage is still important. So there's a lot of talk about the need for capacity, and that's true, and the need for capabilities, and that's also true. But this does not diminish the reality that coverage must be there. The AP must be accessible from the needed client locations. So wherever a client needs access, the client needs access. This is why coverage is still important. In addition, though, the AP must be accessible at the needed data rates. So we can't just say coverage is still important, we have to say the right coverage is important. Additionally, the AP must be accessible with minimum interference. So this is about proper channel selection, making sure that the RF is architected in such a way that we not only have coverage where we need coverage, but we have the right coverage. We have coverage at the right signal strength with the understanding of any interference sources that might be in that space. And we'll get into that a little bit more as we go along. So for these reasons alone, coverage is still important. Remember, though, that coverage is not simple. So for example, covering one client does not equate to covering another client at the same location when allowing low data rates or at some given desired data rate. So let's say your desired data rate is 54 megabits per second. And you then have one client that when it does connect from a specific location, that's what it gets, 54 megabits per second. It's entirely possible that a different client would not be able to achieve 54 megabits per second at literally the exact same pinpoint location. And this is because different clients have different receive sensitivities, different antenna factors, and so forth that end up impacting the data rate they're actually going to be able to achieve at that location. Additionally, changing environments result in changing coverage. So that is to say that some environments are dynamic. Think about warehouses and manufacturing environments and shipping environments where trucks come and go and things like this. These changing environments result in changing coverage because remember, coverage is born not out of just some direct propagation pattern, but also indirect propagation patterns with reflection and other factors as the radio frequency waves move throughout the space. So in these changing environments, it's often best to design for the environment in a kind of worst case scenario related to propagation. For example, when all the shelves in a warehouse are full, or when there are several trucks in the area instead of no trucks in the area, and these kinds of things. So we want to think about that when we're designing for those environments. And then also changing clients results in changing coverage. So you may have built your wireless LAN for a specific client pool, and now you may be getting new clients into the space that may change your coverage perception because you need the right coverage from the perception of those new clients. And the reality is just because they're newer clients does not mean they are better clients from a receive sensitivity perspective. They may have older chipsets in them even though they are newer clients. This is not uncommon in specialty devices. Think of things like door locks and monitoring devices and things like this that might be added to the space. And sometimes they're also added at the periphery of the space. For example, a door lock is obviously at the egress or ingress to the facility, and so therefore it's going to be at possibly the edge of a coverage area and may or may not have the coverage that is required there. So these are the kinds of things to think about when we think about coverage. It's not simple, it's not straightforward. There are a lot of complexities involved in coverage as well. Now, coverage then is the foundation of capacity. So capacity, we can say, is a measurement of the load that can be handled by the wireless LAN, such as the total number of clients or the throughput available per client, these kinds of things. When we're thinking about this capacity then, we really have to understand that coverage must exist for capacity demands to be met. We can't possibly meet capacity demands if there's no signal there. So coverage is easier than capacity, but that doesn't make coverage easy. It just makes it easier. It's kind of like saying lifting 350 pounds is easier than lifting 400 pounds. It's still not easy, but it's easier. Both are complex for new wireless LAN administrators and engineers, and this is why it's good that we have a lot of tools these days to help us out. Things like Ekahau Survey and Tamosoft's Tamograph, and we have Air Magnet Survey Pro and so forth. So there are these different tools that help us to look at the environment and get a visual perception of what our coverage looks like throughout that space. Finally, coverage is technical. To understand coverage issues, you have to understand RF behavior, propagation patterns, for example, like reflection, refraction, diffraction, scattering, absorption, and so forth. These are all covered in your CWNA studies. Power measurements are important to grasp. We'll talk about some of that terminology momentarily. Data rates. We have to understand data rates. We have to understand that data rates are fixed. For example, we don't go from 54 megabits per second to 53.9 megabits per second. You may have noticed that. Why do we make the jump from 54 to 48? Well, it's because data rates are determined by modulation and coding, and a few other factors too that can impact the overall data rate. When considering data rates then, you have to understand that the modulation changes for the simple reason that with a poor signal, you cannot process more complex modulation algorithms. You need a really good signal for that. So the data rates adjust to different modulation schemes in order to accomplish pushing the bits through without corruption or with readability. And then you also have to understand channel access methods. That is, how does a device gain access to the channel? So we're talking here about things like clear channel assessment and the nav timers and these kinds of things, which we'll talk a little bit more about later. So the terminology related to power measurements include SNR. This is signal to noise ratio, and it's a comparison of the signal strength to the noise in the environment. Then there's RSSI, the received signal strength indicator, and dBm, decibels compared to milliwatts. Now, RSSI, technically speaking, is a relative value, but it's often used colloquially in common use as synonymous with dBm. So technically, RSSI is defined one way, but it's commonly used to mean dBm. So for example, you'll hear people say the RSSI is negative 67. Well, what they mean is the signal strength is negative 67 dBm. A device driver may actually report an RSSI of, say, 80 when the signal strength is negative 67 dBm. But in common use, people have begun to use those interchangeably. So you have to understand how someone might be using RSSI. Are they using it in the technical, defined aspect of the term as according to the 802.11 standard, or are they just using it as a replacement for dBm? And of course, decibels to milliwatts is a comparison of decibels into milliwatts, or conversion of decibels to milliwatts, so that it's an absolute value. It's an absolute value. So basically, 1 milliwatt equals 0 dBm, and you go from there. So therefore, 3 dBm would be twice as much as 1 milliwatt, therefore it's 2 milliwatt, and so forth. Negative 3 dBm would be half as much, so it's 0.5 milliwatts, and so forth. It's important to understand that when we see negative dBm values, we're never talking about negative power. We're talking about less power, very, very low levels of power. So when we say that we're at neg 60 dBm, we're not saying that there's some negative level of power. We're saying there's a low positive level of power somewhere between 1 milliwatt and 0, and that's the key, okay? Now, I said channel access is important, and the two big ones here are the nav timer and CCA, clear channel assessment. The nav timer is set according to the duration value in the MAC header. So the nav timer is a layer 2 factor in channel access, and basically it's set by the duration value in a frame that it sees, so it can only be set by a client that can process the frame. The frame is transmitted at a given data rate, so not all clients will be able to process the frame. If they're too far away to be able to process that frame at the appropriate data rate and demodulate it, because what do they not have? A good enough SNR, right? So the signal noise strength is not good enough. They cannot therefore demodulate, but if they're in the area of the BSS such that they can participate in it, then it should mean that they can demodulate the PHY layer headers. So the PLCP header and the PHY preamble should be able to be demodulated. That's going to tell them how long the current frame is that's actually being transmitted. And that's because there is a length value in that PHY header. The CCA idle then is two things. It's clear carrier sensing. The clear channel assessment is carrier sensing, and it's energy detect. So carrier sensing means it's actually detecting a frame. We're looking at those PHY headers. We're seeing that an actual frame is being transmitted. Energy detect is saying, well, I'm just seeing RF energy. Maybe it's 802.11, maybe it's not. I'm just seeing RF energy above a certain threshold. So with energy detect, when that is used, basically the client cannot transmit because it's detecting RF energy above a certain threshold as specified by the physical layer in the standard. When carrier sense is there, it actually does see that frame. It's able to begin to process the frame. Again, it may not be able to demodulate the upper layer payload, which is called the MPDU, coming down from layer 2, the PSDU, as it's referred to at layer 1. So it may not be able to demodulate that information, which is transmitted at a higher data rate than it could possibly process, but it can see the PHY header. So it knows that a frame is being transmitted, and it knows the length of that frame. So the point is, in my coverage area, I need to think about how many clients are going to likely end up being out there that all they really have is carrier sense, and they can't be using the nav timer to help them. The nav timer is set, and the client will not even try to access the medium until it's counted down. And by the way, there's a bit of a misconception about the nav timer and what it is. The nav timer does not contain the duration of the current frame. It contains the duration of any subsequent frames and interframe spaces that are required in order to complete the transaction, such as an acknowledgement frame or something like that that might have to come after the current frame. So carrier sense we've already talked about. I need not go into it in extensive detail, but again, carrier sense, we see an 802.11 frame, energy detect. We're detecting energy above a particular threshold. That's called the virtual, or rather the physical carrier sense. The virtual carrier sense is the nav timer that we've talked about. Now, the channel conditions impact the data rate. So what we have here is the Shannon-Hartley theorem of channel capacity. So channel capacity equals the bandwidth of the channel calculated against the signal-to-noise ratio. So we have this algorithm, the bandwidth of the channel times the logarithm of 1 plus the signal-to-noise ratio. You don't have to really do math to understand the factors here that impact the channel capacity, how much we can push through a channel. It's a factor of the bandwidth. How much frequency space am I using? Is it 20 megahertz, 40 megahertz, 80 megahertz, and so on, and the signal to noise ratio. So the more frequency space I'm using and the better signal to noise ratio, the more I can push through my channel, right? But it's important to know that when you have a wider channel, 20, 40, 80, and we'll see this later, then you have to have a better signal to noise ratio in order to accomplish the highest data rates that channel can support. So for example, here we see for a Cisco WAP371 that there are certain levels of signal strength required by the receiver, this is receiver sensitivity, to achieve particular data rates. So for example, in 2.4 gigahertz, we can get a 54 megabits per second data rate with a neg 75 dBm signal. But we can only get 11 megabits per second if we have a neg 86 dBm signal. Notice for a 20 megahertz wide 802.11n channel, we need neg 69 for MCS 15. But if we want to get MCS 15 with an HT40 channel, we need neg 66, a signal that's twice as strong. Now again, that goes back to dB math, right? So 3 dB is doubling or halving. Since neg 66 is stronger than neg 69, and there's 3 dB difference, we know that neg 66 is 2 times stronger. So therefore, to accomplish the same highest possible data rate in the bandwidth, we have to have twice the signal strength for 40 megahertz over 20 megahertz channel. But it's important to know that that highest data rate is much higher because we now have a wider channel, which we talked about with the Shannon-Hartley theorem. So the receive sensitivity is an important factor in coverage, and I point this out because not only do your APs have receive sensitivity levels, but your clients do too. And so these receive sensitivity levels are going to determine factors related to your coverage. If you want particular data rates, you've got to meet these receiver sensitivity levels. We also have to make sure that we have proper roaming coverage. So this is a very oversimplified example because we don't see ovals or circles as our coverage patterns from our actual APs in most environments, but it illustrates the concept. Notice when this device roams from BSS ID 5F to BSS ID 5C from left to right, it's going to go through a space where there is no coverage according to our needs. Now maybe that space still has coverage by the AP, but it's at a data rate that is too low for the applications we're going to be using. The point is that I don't have the coverage that I need in the path of roaming. So this is a simplified example. In the real world, this is your facility, this is a floor plan, and you're making sure that in the path of roaming, the proper signal coverage is there. Here's an example of good coverage. So now, obviously, our coverage patterns do cover the path of roaming. And again, that's a true physical path through your facility that the client may move. Now, roaming design is better performed based on visible APs at minimum data rates in many cases. So that is to say, when we use our site survey software and we're looking at the coverage produced by our APs, what we want to see in particularly a post-validation survey, but even in the pre-design phase, what we want to see is the coverage such that no matter where we put our mouse in that application, it's telling us, here are the APs I can see from here, and it's always seeing 2 or more APs. That's the ideal. Now that's harder to do in 2.4 gigahertz than it is in 5 gigahertz because you have fewer channels, but that's the basic goal of roaming coverage, to have 2 or more APs visible at accepted data rates at all times. Now, here's the ultimate summary then of this information about coverage. Design for signal strength availability and not for simple signal availability. So what I don't want to do is design such that I have coverage. I don't want to have a simple coverage design model that says, I can see the AP from here. Just because you can see it doesn't mean you'd want to use it. Okay? Think of it like this. The reality is, just because I can see a certain tool available on my tool shelf does not mean it's the right tool for the job. If I need a flathead screwdriver and what I see is a Phillips head, doesn't mean I should use it. In the same way, I need the right AP for the job, and that means I need to see the signal strength at the data rates I need, therefore at the signal strength level I need, the SNR level that I need, and so forth, based on the receive sensitivity of my client and the applications that I'm using. Now, people often say, well, how do you know what signal strength you need? It comes down to data rate, and data rate is driven by applications because of the throughput requirements that they have. So when you define your applications, you can then define your needed data rates. When you've defined your needed data rates, you can define your needed signal strength and SNR, and that's the path you go through to get the coverage that you actually need. Again, as a reminder, our conference is coming up in New Orleans, September the 28th through the 30th. We also have pre-conference training available. You can learn more at cwnp.com/NOLA, and you can get 10% off your registration with the discount code of Wi-Fi Jazz through August 19th. Thank you very much for attending this webinar, and I'll hang around for a few minutes for those who might have questions.